Welcome everybody, and clearly everybody here needs a break after the release of the decadal report today and the press conference that we just had. So here's, we hope, something to take your mind off, either celebrating or crying into your drink. We have Aneta to talk to us today. Aneta came to CFA a long time ago during her PhD work, which she undertook at the Copernicus Center in Warsaw. She worked there on accretion disk theory with Bayesian and Czerny, who a few of you may know from her visits here. I then hired her as a postdoc, and within a few years, she had transitioned to join the CHANDRA X-ray Center. This was still a few years before launch. And after launch, the discovery capability of CHANDRA caused her to change her research interests. She's worked a lot on AGN jets in X-rays, in particular the young jets found in the gigahertz peak sources, and she has now extended that out to very high redshifts of 4 and now 6, I believe. But as part of her CHANDRA X-ray Center work, Aneta pioneered the Sherpa model fitting package. And as part of that, she initiated a collaboration with the Harvard Statistics Department. That's flourished mightily. And so now, instead of being a very minor part of astronomy, it's really quite a business. In fact, now she is president of the International Astrostatistics Association. So that's, of course, why she chose her colloquium today, which is entitled Adventures in Astrostatistics. Aneta.
Thank you for joining me today. And I'd like to thank you, the committee, for giving me an opportunity to present my research. I'd like to thank you, Martin, for introducing me to this colloquium today. Also, I'd like to thank you, everybody, for joining me today, which is not a typical day for us because it's a big day for astronomy in general, looking at towards the next decade. But I'd like to take you on a journey which I undertook almost 2 decades, or actually 2 decades ago. So I will talk about adventures in astrostatistics today, and I will focus mainly on astrostatistics in high energy astrophysics. So this is what I will consider today. And it's mainly because when we look at the X-ray universe looks quite different from the optical universe. You have this X-rays which signals the violent events because you need to have the gas which is hot. So you have something which heats up the gas to this very high temperatures, more than 100,000 Kelvin. And you also have to have an event which accelerates the particles which emit X-rays. So here are examples of the images which were obtained by CHANDRA. So all these images are in X-rays, and you can see that even solar system planets emit X-rays. Then we have supernovae, we have huge clusters of galaxies which emit, and because of the hot gas contained in them, very, very beautiful actually X-ray structures. And of course we have quasars with very long X-ray jets, which were discovered by CHANDRA. And this is what was my X-ray astronomy research started, as Martin said earlier today. So CHANDRA was launched in 1999, and this is the image of the CHANDRA launch. And then in August 12, 1999, we opened the telescopes and the detectors, and we looked at the sky in X-rays. So this is the first CHANDRA image. And you can see here the excitement of the scientists, Harvey Tannenbaum and Martin Weisskopf, the project scientists, looking at the screen and looking at these events, which, you can see mostly the background, but there are also some point sources. So when we looked at the sky, we understood that our detectors and our telescope work very well. So we were all excited. So, this doesn't work. Here. So this is the outline of my talk. I will say a few words about the beginning, but then I will take you on these 4 adventures and talk about our work within CHASC, and then comment on some emerging methodology and future, which we will have here. So when we think about scientific experiments, we usually have different stage, right? You have an idea and you have to propose the observations to study this idea and see if it's work or not. Then we do observations and we collect the data. Then the next step is preparation of this data. The data come back from the satellite and you have standard processing, you look at the calibration and run specific software. And then next, the analysis and scientific measurements are performed by scientists. And then you conclude, you have final conclusion and you look at the image and you think, oh, you know, is this what I think it is, or it's something else? And you, if it's something else and you maybe discovered something, you go and you propose and do next observation. So what's important is that at every single stage in this scientific experiment, you need statistics. So statistics is important and we have to think about it when we do analysis of our data or science in general. So at the beginning, well, when you think about statistics and astrostatistics started in ancient times. And the statistical methodology was developed over a course of 1,000 years. And modern statistics, of course, is very different than the statistics of calculating just means and standard deviations. It's a very rich field. X-ray astronomy started in the 60s, so it's very young, developing very quickly field. And you can see with CHANDRA the discoveries which can be made in X-rays. So methodology, in statistical methodology, which is based on the techniques developed in the past, doesn't directly apply to X-ray data. There are several issues with looking at these old methods, and in the 70s and 80s, and people pointed this out, and I listed the papers, several papers from 70s and 90s, and these papers were, some of them were with collaboration with statisticians. And these collaborations were important because we didn't know how to do this analysis. But somehow there were difficulties. So Eric Feigelson, who is known for advocating the collaborations, organized these meetings between statisticians and astronomers. And at these meetings, people met and talk about it, and scientists talk about the issues. We were invited, our group was invited to actually present the issues which were expected when new CHANDRA data will come down, and we will look at this. So I went to Penn State in 1997 and presented this, actually this was 96, and discussed the issues in the modeling of data, source detection and instrument-related issues at this meeting. And after that meeting, when I came back, Martin and I went and had lunch with Donald Rubin, who was the chair of the statistics department at that time. And we showed him our issues and showed him the paper and asked about the collaboration. So we were fortunate because at the same time, David Van Dyke arrived to Harvard, and Donald Rubin said, okay, maybe he will be interested in these issues. So this is how CHASC started, and this is where the discussions between us astronomers and Harvard statisticians were initiated. So CHASC was formed, and this is our website, International CHASC Astrostatistics Collaboration, and you can go and see who is involved. So since early times, we have a group of statisticians and astronomers, and we try to work together. And we have lists of the people involved and lists of former students. And you can see there's a lot of students who actually worked on astrostatistics research and published their thesis within our group. So you can see them. One comment which I want to make is that our website is very old. It's old HTML, and we are looking for somebody, some volunteer who wants to change this website and bring it to 21st century. So if there is anybody there who loves doing websites, send me email. So we'll talk about it. One thing which we had to do, especially in the early times, is to make this dictionary of words, because astronomers and statisticians have very different language. So on our website, you can also find statistical jargon for statisticians, and statistical jargon for astronomers. And the extract of this page was published in our Handbook of X-ray Astronomy a few years back. But it was interesting because the language which we speak is important for communication. And these early discussions were quite a learning curve for me, because I had to understand what the other side means. And it was fun at that time. But going back to science, right? So we have X-ray data, and collecting X-ray data means counting arriving photons. So counting Poisson counts. This is quite different than the optical data, where we're looking at the bright, intense sources. So we don't think about optical counts. But in X-rays, we count, and each photon location, photon arriving to the detector, has the location, arrival time, and energy recorded in form of an event. So here you see the image, which is CHANDRA Deep Field North image, with a lot of point sources. Most of them are point sources. And this observation took 23 days. And the photon, the faintest source in this image, had one photon, one X-ray photon emitted every 4 days. So looking at such sky and such deep, far away to faint photons, so to lower fluxes, require long exposures, because CHANDRA telescope is very small. You know, optical telescope have 10 meters diameter, and CHANDRA telescope is less than 1 meter square effective area. So you have to observe this sky for a long time to get the information which is necessary to observe, right? To get. So it's one of these X-rays observations which we have to realize it takes a long time. So Poisson counts. I mean, this is the example of the light curve, which comes from the steady source, star. And you can see that this red line actually shows the steady rate. But when you look at the counts, there is the asymmetry in the top versus bottom counts. So when you look at the distribution of these counts, you see that there is the asymmetry. And the counts are integers, and then you have a tail. So this distribution doesn't look like typical normal distribution. And you need to account for this shape when you look at the low counts data. So our first adventure was with modeling low counts X-ray spectra. And you can see that this is the low count spectrum, the top. And in channels, we have very low number of counts, up to 4 in one of the channels, but most of the channels are empty, and then there are some counts. So when you model such data, you include instrument response directly, and calibration impacts on the results. So in the model, you have counts, and you have ARF and RMF, which are the instrument calibration files, and then model with parameters for given energy. And you have to integrate this in order to understand how many counts your source emitted. And conversion matrix between channels and energy is used to look at the counts versus energy, arrival counts versus energy. So this is the rate. The difficulty in analysis or modeling X-ray spectra is also that most of our models are nonlinear models, and many of them are computer generated. So the optimization and finding best fit in this space is quite complicated. But the importance of the appropriate fit statistics needs to be underlined, because we cannot do binning or grouping the data. This is loss of information. If you start binning the data, then you may lose the features which are important for your physics. And we also cannot subtract the background, because when you subtract the background, you may, first of all, get negative counts or generate some features which are not real because they are really from the background. So initially in the 90s, there were several modifications to the standard fit statistics, which was chi-square. And the modifications were in order to make the low counts sort of behave. So low counts be good in these approximations. But also there were formulation of the Poisson likelihood. And this was done in CHASC, who pointed out that we should use those, and then the formulation of C-stat and W-stat. And why was that a big deal in the early 2000s? Well, people thought that when you have the fit, when you fit your model to the spectrum, you have to have some way of goodness, assessing goodness of fit of these models. And the standard approach and chi-square gave you the goodness of fit, which was not really easily accessible with the Poisson likelihood. But more importantly, when you apply wrong statistics, you can see the bias in your response. So this is the simulations which was done for the model with the parameter at 1.28. And we simulated 60,000 counts in the spectrum, and then each of the spectrum was fit. So we had a lot of simulations, but each spectrum was fit with using the Poisson likelihood, which is this shaded region, and then the modification. So this is the chi-square using the model counts weights, and then the standard expression with the measurement here. So you can see this when you use this statistics which are based on normal approximations, Gaussian models, Gaussian distributions, you have the biases in this. So you can't use that, right? So in our adventure, we looked into Bayesian modeling of this low count X-ray spectra. And remember, this was early 2000s, and we didn't know anything about Bayesians. And I remember actually being there and thinking about MCMC methods and Gibbs samplers. And this was way, this is like the ancient times, because at the same time, MCMC revolution was happening in the statistics. So we were sort of at the beginning of the revolution also in astronomy, because after that the MCMC became sort of a standard, right? So we developed this Bayesian framework where we're looking at the posterior distribution of the parameters given our data and our calibration. So A here is ARF, and then we have Poisson likelihood and the prior on our model parameters. So this model is implemented, and it was implemented in Sherpa and also applied in processing of the CHANDRA source catalog data. What was important and nice about this approach was that you can take the full information of your data and your calibration into account. And you can also input your uncertainties on the calibration product into the MCMC scheme and into this Bayesian approach, because in standard approach, which is shown here, we use the ARF as a fixed value, right? But you can imagine that we don't know ARF and we can use it as a parameter. So in addition to model parameters, we could also look at the ARF as one of those calibration unknown or having an error on it, and look at and fit, maybe get the best estimate of your ARF. And then again, likelihood would be based on your data based on the model parameter and given ARF, and then prior on model and prior on ARF, right? So this calibration product. So in the MCMC scheme on the right, which is the standard way you look at the Bayesian MCMC method, you have model and prior, and you draw parameters, compute likelihood, and then accept or reject and update parameters and do the loop. You could put this effective error into the loop and then use the full Bayes approach to actually get this into account. So we did this with 2 students, and actually this method is implemented in Sherpa, and as soon as we have calibration products, people can use it. So the second adventure was related to hypothesis testing and model selection. And when you look at the spectra, this is again X-ray spectrum overplotted with the model fit. This is a simple model on the left, just the power law. And at the bottom, you see data of a model ratio. And you notice there are these features in the data of a model ratio. So these features may indicate that we have a line there. So the second model contains this line. And the question is whether this line is really significant or needed, and whether the model with the line is better than the model without the line. And this is not a simple question, actually, in statistics. And standard approach, which was developed for the normal approximations and assumptions of the chi-square distribution, actually doesn't apply in this case. So in our work with the statistics student Rostisław Protasov, we lay out the reasons for why this is incorrect. So why standard likelihood ratio test or F statistics do not apply in this case. And we also propose the way to do the simulations to calibrate the likelihood ratio test distribution or test statistic distribution, and then use it in the calculating the p-value. We also describe the posterior predictive p-values, which is a Bayesian way to calculate the p-values, where you have the Bayesian model and you include all the information about the priors into that model. So this is this example of Bayesian posterior predictive p-value, which you just simulate the data under the null model, so no line, compute the test statistic for each data set with the line and without the line, and look at the likelihood ratio test. And then you do this histogram. So this is the histogram showing you these simulated values. The line, vertical line, indicates our observed value. And looking at the number of exceed or maximum values which are larger, you can say, okay, it's 1.6% of this value, and but our model with the line is better than model without the line. This is again included in Sherpa. I'm advertising Sherpa because that's what, as Martin said, was my main reason or my main task when I was working, started working at CHANDRA X-ray Center. So this single detection of the line was extended later on, and we looked at searching the line. So in the long-term spectra, you may have a lot of features and you want to understand whether there is many lines or one line. So when you use the high posterior density plots like this, you can find the location, most likely location of the line. And this one at 2.84 kV, then you can run the test similarly to this test which I just described and calculate the PPP value for the fixed location or for unknown location, which is of course more difficult test because you don't, I mean, it's very hard to find the lines in this spectra. Okay, so this was the spectra. Now, when you look at the images, I was showing you the X-ray images, which are beautiful because they had a lot of counts, but these faintest sources are important. And sometimes you want to understand whether your source was even detected. So the discussion on upper limits in source detection was presented in Vinay paper. And this discussion, I'm not going to go into the details, but this discussion and the results which are written in this paper took a long time. We went to SAMC meeting, we had big discussions within the large group on defining upper limits versus confidence bounds, and all this is contained in Vinay's paper. I just focus on one aspect, which is the hardness ratio. So when we have faint sources and not enough counts to do spectral modeling, which I was just discussed, we typically use hardness ratio calculations. And the hardness ratios calculations in X-rays are similar to colors in photometric ratios in optical. The problem is that our hardness ratios are based on very low counts. Again, it's Poisson counts we're looking at. So this was a fun, well, good adventure as well, because again, Bayesian approach helps, and it was implemented in Bayesian estimation of hardness ratio code by Taeyong Park, who was our student at the time. So you have simple ratio, which is just ratio of soft to hard counts, for example. There could be a color, and there could be a fractional difference, which is typically used in X-rays. So hard minus soft over hard plus soft counts. In classical approach, you also have a background which you subtract, right? And then this is the modification of the equations. Then you have to propagate errors on this subtracted background. So these are the equations, and I don't want you to read them, but these are the equations which are contain these scalar errors on measured counts. So this approximation, which is listed here. What's important is that this difference between classical and Bayesian approach shows you the difference in high counts regime, where both approaches differ not a lot, right? There is some difference, but maybe not hard. But when you go to low counts, which is here, so this is a ratio, simple ratio, and the probability density function. So for Bayesian, you have this skewed distribution, and you can look at the widths of the distribution when you think about the error. And in the classical approach, you basically have a huge flat error which completely misses the Bayesian. So you overestimated the error on hardness ratio. And the same is with hardness ratio typical for X-rays, where the issue is with the bound between -1 and 1, because you have bounded values, and then the estimating of the errors in low counts is quite basically impossible in the classical approach. The code again is available, and this Bayesian approach is applied in the processing of CHANDRA source catalog. So the errors which you get in the catalog when you get your sources are correctly calculated with this approach. But as I said, CHANDRA is a small mirror, but it has the best point spread function, so the best angular resolution of the X-ray X-ray telescopes available to us. So takes the highest resolution X-ray images of the universe. The problem with these images is that they are very sparse. So this is the typical image where you can see the source and you see some smooth structure around it, but a lot of pixels in this image are empty. And also the PSF, so point spread function, so the way you see the point source in the image is different depending on where you are on the detector. So that's the variable across the PSF, which means that the analysis of these images are not trivial. And we have issues with detection of features and upper limits, as I already said, but also detecting and identifying low surface brightness structure. So here you have the CHANDRA image of the galactic center, where in July 2004, we had a magnetar flaring, and you can see there is like many point sources, but also maybe the smooth emission. The magnetar disappeared in July 2005, and you still have a lot of emission, which is kind of busy and untangled, right? So resolving sources in this image is tricky and not trivial. We have overlapping sources, and we also don't have an easy way to find a boundary of this structure, which is smooth, right? The tail of kind of filamentary structure. So these are the issues which are not easy to tackle. And we started with the looking at the high resolution X-ray images in a Bayesian way and trying to understand the shapes of the structures in the low counts images. So you have CHANDRA image on the top, on the left top, where we have the bright source and then some distribution of low surface brightness, but these are all individual counts. There is a PSF, CHANDRA PSF, which is plotted here. And we assume that we just have this CHANDRA, so this point source, like quasar in this case, and some background, which is actually lost in this dark image. So we have this, this input, and then we run the Bayesian hierarchical model in which we try to understand, so using everything, all the information and looking at the realizations of our model, the parameters, and we draw posterior images using MCMC. So here you can see the realization. So we run MCMC for 1,000 times or more, and in each image you can see that some of the pixels are highlighted more and stay maybe not visible, and some of them vary a lot. When we take a mean of these images, we see the structures, which are sort of wiggly structures. And the question is this wiggly structure real, or is it just something which we imagined and MCMC brought it to us, right? So we looked at this posterior mean and then developed a way to find the sort of the locations in this MCMC output images which are related to each other. So we're looking at the probability distributions of the pixel assignments, and the correlation between the pixels is described by Ising model, which I'm not going to go into details, but well, what you see now is the probability distribution of the pixel assignments which are close to each other and can tell us about the optimal boundary of the structures which are present in the image. So this is the boundary, so we can see the little pixels highlighting, and they contain the maximum probability of being there. So having the signal given our linear Ising posterior from this relatively complex model. So at the end, when you apply the maximum probability, you can find this, these are little red islands, which look like knots in these wiggly structures. And those are potentially the knots in the jet, which is visible in radio. So from radio, we have this previous knowledge of the knots in this source. In CHANDRA, without the LIRA, just looking at the CHANDRA image, we can draw the regions on this image based on the radio, and then using just the first step of the model, calculate the significance of these structures given just the simulations which we have, so MCMC images. And the test statistics which we define to calculate the significance of the structure was described in this Stein paper and then used by Katie McCall to calculate this, the quasar luminosities or quasar jets present. So you can see that given the test statistics defined here, we can have structures in region 2, which is here. There is very strong blue line indicating our source. And for region number 1, there is no such structure present. Okay. This is in very quick words describing very complicated model actually and very complicated structures, but details are there and you can ask me later. So I talked about adventures so far, just to summarize quickly. We talked about low count spectra and sparse Poisson images. But X-ray analysis so far was done in this single domains. You notice that I talked about X-ray images and about X-ray spectra only. I didn't say anything about light curves. But when you look at the high resolution X-ray images which CHANDRA gives us, we have more information than just the image. We have information about the location of the elements in the supernova. So in this case, we have iron, which is located in different parts of the supernova. And we have also the argon, which is also located in different parts of the supernova. So what you want to do is to bring all this information together, not analyze this separately, separate spectrum and separate image. You have to, because we have the information, we want to use this together. So there is a new, this is actually new. There is several new emerging multi-domain analysis, and this is what's happening over the last few years. So in spectral image, when you have this information, what you can do is to recover the elements in the stars before the supernova outburst. So you can actually start thinking about complex physics when you have more information in this data. In spectral time domain, there is of course lots of information right now, but we're looking at spectral and timing and looking at the correlation between different wavebands. So the lungs give you the information and the cross spectrum gives you the information. So this is a new era, and I think mostly because of very good, nicer observations, there is a lot of progress in AG and science looking at this reverberation methods. And also in image time, when you look at this Crab Nebula, it's not steady. This source is very dynamic. So in order to study the physics of this dynamic system, you want to be able to analyze the image and time at the same. So if you have a model which you can apply, like your physical model, you want to be able to apply it to this type of data simultaneously. So I just want to point out briefly two methods which are emerging to actually use the full information about spectrum time and image. And these two examples will be related to the resolution of sources in the crowded fields. So the field like Orion, which is plotted here, has a lot of stars, and some stars, because of the PSF, cannot be separated. So you want to be able to actually study the stars which overlap. So that's one example which I show soon. And then the second one is about the using change point time series to actually do the image segmentation and then analyze the changes in the image. This is example of the EBASCs. So that's the this is the binary system on the left, and you see the red and blue stars locations and a lot of individual photons which are spread around. So looking at the information in spectrum and variations, you can separate the photons and understand which photon comes from which star. They have very similar spectrum, so blue and red, but when you look at the variability of these two sources, you see the changes. They vary in a different way. So red star is mostly like going up and coming down, but blue star comes down and then recovers. So you can have light curves of the individual sources. And then you can also look at the spectral variations across the time in these two sources. This is a little bit more complicated because we don't have enough spectral information. So what you're looking at is the ratio variation. So soft versus medium band here, and how this star, so red star versus blue star, how they the hardness ratio changes in time. So the top one shows the intensity of the stars, and the bottom shows the changes in the hardness ratio. And you can see that at some locations, the spectra of these two stars are very different. So this is a great result, I would say. And then the second method, which I like to highlight, is this is XMM data of Proxima Centauri. And the light curves, so counts versus time, show the change in behavior, which is marked with this blue vertical lines. So you can pick up the interesting part, and this is the time 42, which is plotted up at the top. So you have an image at time 42, and you have a model image of this source at time 42. What you can also see is the time before, which shows the increase in intensity of the source, and time after, so time at 43, where you see the decrease in intensity of the source. So you can pick up these changes looking at the four-dimensional information present in this X-ray data, which is quite exciting. So what I like to point out that there is also a future in full multi-domain analysis as presented in these two examples, where we can look at spectral time image and think about supernova and develop very complicated physical model and maybe find a way to look at it in the data. There is also a new domain coming up when we get polarimetric observations, and then we will have to figure out how to actually look at the X-ray polarimetry in a nice way. So this is a very new domain, which is happening right now. So this is the quick summary of the adventures. So that's what I said about the past and about what we try to do over the last two decades, but there is the future, right? So we have this full multi-domain analysis, which maybe solve the problem of supernovae, but there is also rising interest in methodology and recent advances in likelihood-free simulation based methods and computer science and application of machine learning and artificial intelligence will find ways to our analysis, I'm sure. It's just we need another decade for this. We wrote several Astro white papers, Astro 2020 white papers, And when we read the report today, some of this were taken into account. So, we will have a place to develop our methodology, looking at the archival data, looking at the data which we have in hand, and perhaps we'll have this new adventures, I would say. So the future, the steady growth of the field. As you can see, I put the ADS results when I put words Bayesian and X-rays together. These are only UpJ, mostly notices, and ANA. And from 2000, we did several papers up to a lot of papers over the last two years. Collaboration with statisticians and computer scientists is definitely necessary because the models are becoming more and more complicated. The funding to support research in astrostatistics is definitely needed and maybe will come with the new direction after Astro 2020 for education and curriculum. What's nice is that there are some faculty jobs in astrostatistics now, and in this month, AA's job register, there are 3 faculty job posting. One is in New Zealand, if somebody wants to move away from everything and go to New Zealand. That's a very good place to be. There are many astrostatistics organizations which are quite new, and you see that all of them were formed in last decade. The main activities consider newsletters and seminars. There is a new seminar which is joined between International Astronomical Union and International Astrostatistics Association, and the next seminar is on Tuesday next week. And we have also CHASC seminars, our local seminars, which we will continue organized, and we had them. I think we have the record and archival links to all of them 10, 20 years ago. There is Astrostatistics Interest Group Student Paper Competition 2022, with deadline to submit this paper on December 13. And the first such competition was held in 2019, and this is 3 years ago, and this is the nominations at that time here. And these are references to the papers which I described earlier. I will leave this later. And what I want to do at the end is thank you, CHASC, of course, and my long-term collaborators, David Van Dyke, who is now at Imperial College, Zhang Meng at Harvard Statistics, so our 2 statisticians, and Vinay Kashyap, who is here at CFA and with whom we collaborated over this last 20 years. Our website is there, and I'm looking for volunteers to help us redesign. I should also say that the CHASC would not be possible without CHANDRA X-ray Center support. So original work which was performed was really funded by CHANDRA. So first few years before we were able to obtain NSF grants and now NASA ABRA grants. So CHANDRA had a big contribution to our foundational years, I would say. And I'd like to thank you, CHANDRA, for that too. Thank you, everybody.
Thank you, Aneta.
Thanks. Yeah, I hope this.
If I can see myself. We already have several hand raised. Pepe is first.
Okay. Hi, Aneta.
Hello.
I just wanted to make a comment for people here who don't know. The CHANDRA software you mentioned, Sherpa, is being benefiting from this astrostatistics. And another thing I want to mention is the CHANDRA source catalog, because the CHANDRA source catalog properties, and here we have properties for 370,000 sources with CHANDRA, were derived using the Bayesian approach. And we serve properties based on source, which include the full data cube for the source, but also spectra with calibration, hardness ratio, and light curves. And all of this can be used with data mining's approach to find very interesting results. And I know for one, Rafael Martinez Galaza has been playing with it and finding lots of anomalies. We have hidden in there really a trove of treasure that I think you all guys should try to use it. If you're too old to use it, get your student to use it.
Thank you, Peppy. Yes, I know. I mean, this is the CHANDRA source catalog has many of the cutting edge tools implemented. So the MCMC and hardness ratio errors and spectral, the MCMC draws and stuff. So yeah, it's good. It's more. There is more to do with this data.
Excellent. It's great to see what came of having lunch with Tom Rubin so many years ago. So you mentioned the decadal report, and it says nice words. Did you find any line for funding in there of this kind of work, for techniques? I haven't seen it.
Well, I think, it's not directly, because I think there's no specific program which was suggested to be funded. There is the archive research and the collaboration between the archives and the need for software which is related to data is mentioned in the archive. So I think the implementation of this recommendation, it will take actually time to digest what it means and what it will mean for the agencies, right? Because this is where we are. I should add that over the 20 years, so at the beginning of our astrostatistics collaborations, when we had the workshops at AAS, we had just us in the audience. So there were 10, 15 people. We had lunches and we had our own discussions. The recent pre-pandemic meetings where we have astrostatistics sessions or topic in astrostatistics were full of people. So there were, hundreds of people, and in some cases there was no space in the room. So I can say that over 20 years we definitely have more interest in methodology. The funding is still not there because there is no specific programs where you can apply. There are programs on the mathematical side in NSF, but not on astronomy side. And in NASA, there is a new move to support open source software development. But that software, it's not algorithm. It's very different when you think about implementation of the algorithm versus research, which is actually figuring out what is the appropriate way to deal with the problem in statistics and in astronomy. And in statistics, I must also say that our statistics colleagues gain information and gain something from our collaboration as well. And I didn't say anything about the statistics side because that's a different discussion, but it would be nice to have that view presented as well.
Right. Do they in fact find that there are applications of these techniques in very many other fields? Or?
Well, so one example I always say is the point spread function, which apparently for us is something which we use, but in one of the grad student work with genetics, the division of the things were just cut. There was no uncertainty associated with the strains, and he actually got the idea of using PSF example to deal with his problem. So there is an implementation of point spread function into genetics. At least that's one nice example, but there is more. There is some of the MCMC techniques which were implemented by students. were used. So yeah.
Excellent. It's quite late, and I think unless there's another question that's urgently up, I'm afraid we have to come to an end. So let's thank Aneta again.
Thank you.
Thank you.